Excellent. I want to begin with our slides. Okay. I'm going to begin with our slide deck for the evening. So today we're going to be talking about clustering. Clustering is unlike anything you've seen before in this class. Again, its main difference is it's not predictive. Nothing we're going to do today is predictive. Now we'll talk about how we can use cluster analysis as a precursor to predictive analysis, but clustering as its own model is not a predictive one. So where we are in this two-way table of machine learning is in the bottom right. We're going to be looking at an unsupervised model, and we're going to be looking at when most of our data are categorical, i.e. they're categories, they're finite. This dimension reduction is another class. So we're going to hit all four of these in the course. Today we're going to be focusing on clustering. So, what is a cluster? Someone give me a definition. Doesn't have to be mathematical, doesn't have to be machine learning oriented. What is a cluster? What is a cluster of people? Yeah. Group of objects that are similar in some way, right? If I say that we're clustered, you immediately think things that are similar to each other. So it's a group of similar data points. It's its most basic form. The concept of similarity, though, is central to this whole idea of clustering. I.e., I can change what I mean by similar to. I could have a cluster of data science students. You're similar because you all are taking data science. I could have a cluster of men and a cluster of women. They're all different now they're all similar to each other for different reasons. So I can change what I mean by similar and change the entire clusters automatically. In general, a greater similarity between points means that they're better clustered. So if I can say that two points are very similar, that means they're very well clustered together. So what's the purpose of a cluster analysis? Why does it exist when we have predictive analytics, which are so cool, and they answer cool questions? Why do we even have cluster analysis? Big answer, to enhance our understanding of a data set by dividing the data into groups. So more often than not, in the real world, you're going to be handed a piece of data, i.e. like last Wednesday, and you're not going to know what the hell to do with it, first off. You're not going to know what to do right off the bat. Now on Wednesday, I was nice enough to tell you what your response was, what you were trying to predict. But that didn't stop some of you from taking it a different route. Some of you actually tried to do a preliminary cluster analysis by saying, okay, well, what makes all the Italian cuisines Italian? Like, what makes them similar? And as soon as you ask that question, like, what's making this thing similar, you're asking the question, how are they clustered together? You know, what makes someone commit arson or larceny? You know, what makes a stock go up? What are the patterns? So cluster analysis is all about trying to find out how data points are similar without a question being in mind. Because a question generally leads to us, the self-fulfilling prophecy. What is a self-fulfilling prophecy? Anyone know what self-fulfilling prophecy is? Self-fulfilling prophecy.
It's self-explanatory.
It's self-explanatory. So it's similar. The self-fulfilling prophecy essentially says if you have a question in your mind, no matter what you do around it, your mind tends to want to gravitate towards that answer because it's already in your head. So the whole point of unsupervised machine learning is we get rid of that question for the time being and don't let it affect our analysis. We want to explore the data as a whole without having to focus in on a single response variable. It provides a layer of abstraction from individual data points. Essentially, if I give you a data set with 1,000 columns, 1,000 dimensions, clustering provides a layer of abstraction. So, example, humans. All of you have thousands and thousands of predictors about you, But if I say, women over here, men over here, I've provided a layer of abstraction that just made men and women. I kind of ignored the other thousands of predictors, and I made this layer of abstraction and said, all right, all of you complex humans, I'm going to cluster you all in one of those categories. So it provides abstraction like we would normally think about abstraction. The goal is to extract and enhance the natural structure of data. So today we're going to be working with some music data. And the music data is going to have a lot of attributes about it. So what I'm going to ignore entirely about the music is what it sounds like. In the data set, I don't have audio. I don't have any of this. All I have are, influenced by Latin roots, how much percussion is used, how much this and that, beats per minute. These numerical and categorical quantifications of the song are what I'm focused on. And the goal is, can I find out what makes songs similar without having to listen to anything? Clustering is very useful, not just in music, but in genetics, consumer internet, in business. For example, what we were actually looking at, it's kind of hard to read up here, but you should be able to read it on your screens, is it's actually a genetic frequency based on heritage. So we're actually looking at, from left to right, is a frequency of certain gene expressions across people who live in several geographic areas. And the idea here is, well, can we find what makes us all similar? Can we find that layer of abstraction in our DNA that makes us all clustered together? And i.e., thereby pinpointing what makes us different. What are those genes that cause these fundamental differences in humans, and can we manipulate them for our benefit? Genetics, consumer internet. I mentioned Pandora, we'll be working with, but news, movies, all of these things that have all these predictors. In the news, is it about Iraq? Is it about Iran? Is it about Barack Obama? Is it about the Taliban? All of these things are predictors, but there's a layer of abstraction. Is it about foreign policy? So foreign policy becomes this cluster topic that abstracts one layer above all these really nitty-gritty things. Recommendation engines are built largely on top of cluster analysis. So if I can understand what makes a news article a news article, I can understand if it's right for you or if it's right for you. If you seem to like foreign policy, if you seem to like the Taliban, well, not like articles about the Taliban and Iraq, you might like articles about Iran, because they're all under the same cluster of foreign policy, the Middle East. Business is really interesting, the way cluster analysis is used in business. I went to a marketing conference once, and I was so horrified I never went to a data-driven marketing conference again, because if you ever go to a data-driven marketing conference, the only thing people will talk about are how do we cluster humans together without actually talking to them. And it's terrifying, because every single talk is, I was able to cluster people with this metric. I was able to cluster people based on this metric. And then I'm like, okay, you just forgot the fundamental point of marketing, which is these are all humans, not data points. Anyways, in business, cluster analysis is used to understand your mentality, because human behavior, as those of you who worked in the crime data, is so hard to predict. It's much easier to categorize you and figure out what cluster of person you're in to make sweeping generalizations about you. Young millennial, or starving artist, things like that, or hustle bustle entrepreneur. These kind of categories and clusterings and similarities allow business owners to make sweeping generalizations about the public and thereby make business much more efficient. So there's a lot of kinds of classification procedures. Our class will be focusing on k-means clustering, which actually ends up being a very popular project idea. So if you have data that are very interesting and very inarticulate, and if you ever have to ask yourself the question, I'm not even sure what I'm supposed to predict, but this data is still cool, clustering might actually be what you want for your project. So it's an iterative method that partitions a data set into k different clusters. And here's how it works. So, work. First, we're going to choose k initial centroids. So k is a number that's chosen beforehand, just like in KNN. So we have to first choose k. And now you're thinking to yourself, how do we choose k? Well, that's going to be a grid search, and we're going to get to that. For each of those k, we're going to randomly choose k centroids. What is a centroid? A centroid, very loosely speaking, is a center of a data point. So if I have several data points here, 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 data points, the centroid would be a single data point that represents the average. So maybe about here, I would put a centroid and say that is the average of this cluster. Fair enough? Fair enough. I'll get into mathematical definitions very soon, I promise. So we're going to choose centroids for each point, for each data point. I'm going to find the distance from each point to the nearest centroid. Of those k centroids I put there, find the distance to the nearest centroid. Then you assign that point to that centroid. I belong to centroid 1. I belong to centroid 2. And then, for each of those centroids, based on those assignments, it readjusts itself and the process begins again. Got it? Good. Just kidding, here's a picture. So how do we choose these initial centroid positions? Because arguably some of you are asking, well, how did we just randomly put them there? Well, it's random. The most common option is to just put them in the graph randomly. The problem with that is it might yield divergent behavior, i.e. there might be a cluster that goes rogue and never gets assigned to anything. You could assign a cluster based on a preliminary clustering task. So do clustering in order to define k for kmeans clustering. But that is much more complicated and much more time-consuming and much more computationally intensive. So we're just going to put them randomly. And you'd be surprised, that's actually pretty much most common behavior and yields 98% plus fine results. You could start with a global centroid, and then essentially put that centroid as far away from the last centroid as possible. And you keep putting them really far away from each other. The problem with that is, if your data contains a lot of outliers, you might yield divergent behavior. Because the idea of this is you keep putting the centroid to the farthest data point, where the farthest data points are. And if you have a lot of outliers, that are going to be really far from all of your data. So generally, random is fine. All right, how do you determine what centroid a given point is most similar to? So like I said, the similarity criterion we choose is really important. In kmeans clustering, we choose the Euclidean distance. Our good old friend the Euclidean distance, as we've seen time and time again in KNN and other scenarios, we will use Euclidean distance to determine how similar 2 points are. If the Euclidean distance is small, they're similar. If the Euclidean distance is large, they're not similar. How do we recompute the positions of the centers? Well, you do it by calculating the centroid. Now, the centroid calculation is fairly simple. So, has anyone calculated a centroid before? I don't know what a centroid is. What is a centroid? Yeah, okay, it is. How do you calculate the centroid?
The center of mass.
How do we do that? What if I have 2 points? Let's call it easy. 1, 2, and 3, 4. What is the center of mass or the centroid? Add them up and take the average. So I would take 1 plus 3, which is 4, 2 plus 4, which is 6, and then I divide that by the number of points, giving my centroid at 2, 3. Visually, I have 1, 2, I have 3, 4, and then 2, 3 is my centroid. This might look familiar from middle school. It's called the midpoint formula. Right? These meaningless things are now popping up again in the real world. This is the midpoint formula between 2 points. And it extends for any number of dimensions. All you do is add them all up and divide by the number of points you have, and that's your geometric center. It's quite simple. And it does put a point right in the middle of everything. And we keep doing this process. Put it in randomly, assign points, calculate centroids. Assign points, calculate centroids. Assign points, calculate centroids. We keep doing this over and over again until we meet some stopping criteria. That stopping criteria can vary, but essentially, as soon as your centroids stop moving, or move very, very little, arguably with no difference whatsoever, you stop, and you've achieved your clusters. Here's what it looks like. So we have these points, all these gray points. So the first thing I'm going to do is I will choose K initial centroids. Random. I have red, blue, and a yellow centroid. The next thing I do is I assign each point to its closest centroid. Now right off the bat, you're noticing something. This guy right here, bottom left, he's assigned to the wrong centroid. Because, and you say in your head you said wrong. And wrong is very relative. Now you said wrong because you want this dot, this bottom left dot, to be with its friends up here. Because it looks like they should. Right? It looks like they belong together. And how is kmeans going to figure that out? Is what you're asking yourselves. But right now, that guy in the bottom left is assigned to yellow. Let's call it the mean stepmother. Yellow is now assigned to this dot because randomly it was put near it. Fine. So right now, our blue cluster has 4 dots. Our yellow cluster has 4 dots. Our red cluster has 3 dots. I'll assign each point to the nearest centroid. I color them just to make it visual. So now I have yellow points, red points, and blue points. Now I recalculate my centroid. So in the next slide, what's going to happen is, for the red points, all 3, I'm going to calculate the geometric center, i.e. the center of mass, called the, centroid. I kept trying to say inertia. It's a different word. Centroid. Calculate the centroid of the red, the centroid of the yellow, and the centroid of the blue. And these crosshairs are going to move. Here. You see the crosshairs have now moved. The red crosshair is now in the middle of the red points. The yellow crosshair is as in the middle of the yellow points as it can be. Notice how it's not right in the middle, in the white space in between. It's because, think of it like gravity. Right? Center of mass, gravity, it's all making sense now. If I have 3 planets pulling something and 1 planet pulling something over here, these 3 planets win, and it's going to pull that thing closer to the 3 planets. So think of it like gravity, that geometric center, that centroid. Think of it like if those dots were a planet, where would that thing end up if it were all being pulled by its gravity, or magnets even? Think of it like a magnet. So I move the centroids, and now I do it again. I calculate for each point its closest centroid. So now, because the yellow crosshair has moved towards these 3, that frees up this bottom left dot to now be closer to its friends in the red cluster. So I do it again. I assign each point to its nearest centroid, Now on the next slide, the clusters are going to move again. Because the assignments have changed. The yellow cluster has lost a dot, and the red cluster has gained a dot. So the clusters are going to move again. This red crosshair is going to move it to be in the middle of these four. These yellow ones are going to move to be in the middle of these yellow, and the blue ones are going to be in the middle of those blue ones. Now I'm going to ask you a question to see if you follow me. One of these crosshairs is not going to move. Two of them will. Which crosshair is not going to move when I move to the next slide? Which one's not going to move?
Blue.
Blue's not going to move. Why? The math did not change for blue. It's the same four dots it had in the last time I did this. So when I go to the next slide, here, only the yellow and the red clusters moved and the blue one did not. Now if I do the process again, every single cluster would be assigned to the same exact dots they're in now. So this is our stopping criteria. Our clusters will not move if I do this again, therefore I stop. And that's how k-means clustering works. We initially randomly choose those centroids and keep moving clusters towards the dots like they were planets with gravity, and then stop when they're all settled. So how do we know if we're doing well? Right? Because in predictive analysis, we have accuracy, root mean squared error, we have all these metrics to say you're right, you're wrong, specificity, sensitivity. But the problem here is there's no question. There's no response. Those were just data points. There wasn't an X and a Y, that didn't matter. So how do you know if I'm doing well? In general, k-means will converge to a solution, even if there's no natural clusters. So the algorithm I just described, 99% of the time, will stop. The algorithm will say, I am done, even if there's no natural clusters. So we still need to be able to define what makes a good cluster. Because the algorithm will end even if there was no natural clusters. And we'll see examples of those, what it looks like. So there are two validation metrics that are really useful for clustering: cohesion and separation. Cohesion, it measures clustering effectiveness inside of a single cluster. So inside of a single cluster, we essentially have the sum of every point's distance to the centroid. Add them all up. So cohesion is what you get in a single cluster. The cohesion of a cluster is the sum of the distance between every point inside of the cluster and the centroid of that cluster. So do we want a cohesion generally? Do we want a smaller or a larger cohesion? Smaller, right? Because if it's smaller, that means the distances between every single point and its centroid are tiny, which also implies that every point is close to each other. Because in clustering, generally, you define your cluster as doing well if the points inside of it are close to each other. So there's cohesion inside of a cluster. Then we have separation between clusters. The separation between the clusters is very simply the distances between their centroids. So however far their centroids difference is, that's how far apart those clusters are. Simple enough. So here's a photo. On the left, we have cohesion. So the distance between every single point in its cluster are all added up. And on the right, we have two clusters, and its separation is not defined by the points inside, but only by the centroids. The distance between the centroids defines how separate those clusters are. Yes?
Why the sum and not something that will take into account different number of points?
Good question. So why not like a root mean squared error type of thing, like mean squared? The reason is, well, first of all, it's a good question. The main reason is in root mean squared error, the reason we square the error is to penalize it.
Sure.
Penalize only makes sense if there's an answer and you're wrong. Here, there's no right or wrong. In an unsupervised model, there is no question, there's no answer. It's hard to penalize something just because it's far away from its centroid. So, the reason we tend to use non-squared metrics in a clustering algorithm is because we don't want to penalize this point for being too far from its centroid. We really are just curious about how close they are to each other. And the squared metric takes away from the emphasis of how tightly packed are those close points together. To put it another way, if all these points were really close, and one cluster, or one point rather, was like far off in the distance, the square would make it seem like, oh, the cluster's doing terribly. But really the cluster is doing fine for the other 10 points, it's just that one point is really far away. So we don't want to penalize the whole cluster just because there's one outlier. Because that outlier doesn't mean that it's wrong, that it's far away. The cluster could be, this is this squiggly cluster. I could draw this entire quadrant off and say, well, really this whole area is my cluster. So just because a point is far off in the distance doesn't make it wrong. So clustering has a lot vaguer concept of right and wrong. So we don't tend to penalize it harder because there's no question that it's getting wrong. We don't know where the boundaries are. This isn't supervised. It's really unfair to penalize data points when we're not comparing it to a known answer. There is no known answer.
What about like a mean instead of a sum?
What about a
So
mean?
you talked about like roots and squares. What about just instead of taking a sum, taking a mean distance from the center? Because that's like if I have one cluster that has like a million points that are really close, and then another one that's kind of far, fewer points,
Right.
you might have weird things going on.
I understand. We're actually about to do a metric that takes the mean of all of the cohesions. So the question is, why don't we use mean instead of just the pure sum? And we actually do use the mean. We use the mean when we're averaging out across all clusters. So we use a raw sum for one cluster, and then when we extend it out to the entire graph, we use a mean for that exact reason.
So that you can't really compare clusters.
Not with just pure cohesion, correct. Not with just pure cohesion, yeah. When I define cohesion for the entire graph, it is a mean. But within a certain cluster, it's just the sum. And here it is. So, a useful measure that combines the idea of both cohesion and separation. So I can define cohesion for each cluster and separation between each cluster. Well, that's kind of difficult, annoying. I want a metric for the whole thing. Here it is. It's called the silhouette coefficient. And here's how it's calculated. For each point, xi, the silhouette coefficient for that point is bi minus ai divided by the max of ai bi. So what that means. ai is the average in-cluster distance to xi. So it's the average distance between every other point in xi's cluster and it. Average, mean. So we're taking the mean of the distance between every other point and xi. On average, how far away are its brothers and sisters? That's A. B, Bij is the average between cluster difference between xi and the cluster j. So if I have cluster j and this one point over here in this other cluster, I take each point and find the average distance between cluster j and xi. So I have ai, which is the average in-cluster distance, bij, which is the average between cluster difference to xi, and then bi, which is the smallest one. So if I have 10 clusters, for a point xi, here's the question. If I have 10 clusters, how many in-cluster averages are there? I have 10 clusters. 10 clusters, how many AIs are there? How many average in-cluster different distances are there? Ozzy? If I have 10 clusters. Sorry? 10? Not quite. For 1 xi, is 1, right? There's only one cluster it's in. So for 1 point xi, there's only one average in-cluster difference. How many between cluster differences are there? 9. Every other cluster gets a between cluster difference. And BI is the smallest one. BI is the smallest distance to the nearest cluster. All right? So, on the numerator, BI minus AI, if you have a good cluster, think about a good clustering, like a nice tight group over here, tight group over here, tight group over here, and they're all separate from each other, and they're all nicely clustered together. AI, average in-cluster difference, is that small or large? If it's good, small, right? What about B, average between cluster difference? You'd like it to be larger. You generally think that a good clustering puts you away from the other clusters. Like, we're not similar. We're similar to each other, but not to you, for some reason. So generally, you prefer B to be large. And then the bottom, the max between AI and BI. Well, actually, let me back up one step. BI minus AI. So we just described small a is good, big A is bad. Big B is good. Small a is good, big B is good. Yes. Does that make sense so far? Small a good, big B bad. So if the numerator, just the numerator, if the numerator were large, is that good or bad? It's a large number. Good, because that means B is big, A is small. When you subtract them, you get a big number. Fair enough? Going to be negative? Yeah. Ooh. Haha, we're split here. Think about it for a minute. Take a minute to, can BI minus AI ever be negative? Just think about it. Just think about it. Overlapping. Think of that too. Think of it and think about it. Can BI minus AI ever be negative? I love this. Hold on, take a minute, hold on. Let everyone else think. That's a good question.
So what's the worst case clustering scenario would be like a lattice, right?
Say it again?
The worst case clustering scenario would be like symmetric, like perfectly symmetric in every direction.
Perfectly symmetric in every direction.
Everything is equal in distance from everything else, like every point. Like a green.
Yeah. So, but can it be negative? So can you have a negative number?
I don't think it can be worse than that. I don't think you need a negative.
Right.
Is that a no, like you know, or I have no idea? Time's up. What do you think? Who says can't be negative? Cannot be negative. It's got to be between 0 and up, right? Who says it can be negative? Don't be shy, TAs. It can be negative. It can. It can be negative. Think of it this way. Think of cluster. So if it's negative, that means A is larger, right? Because B minus A, if A is larger, then it's negative. So when would A, the in-cluster difference, be bigger than its between cluster. How about these guys? Here's some circles, 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 circles. And here's the circle cluster. Here are the x's, 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 the x's. Here's a cluster. Here's a cluster. They don't overlap. Sorry, I did not mean to make them overlap. The average in-cluster difference here is quite large because the center is over here and we have points everywhere. But between, let's say we're looking at this guy right here, xi, but to the next one, it's quite small. But on average, it's far away from its brothers and sisters. Yeah?
But that wasn't done using kmeans.
How do you know?
I wouldn't think it would produce those results.
X's, 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 X's. Here's the X. Sure can. This point can be closer to this one than this X, barely.
Yeah, but the end result.
The what?
End result.
End result?
The average.
Like if you keep doing the refinement, wouldn't there be two clusters, one on the left, one on the right?
There are.
So like you added those x's over there.
Yeah, to make a point. Yeah, but yeah,
Before
to
you
make a
add
point.
those x's, I guess I'm so confused as to how you would get that clustering effect of all those zeros there and these x's here.
Because this X is just, like, for example, like this is between this X is like 9.9 and this is like 10. It's just closer to this one than it is that one. Barely. Yeah.
What happens if there's one right in between, like really indifferent to clusters? Which cluster would you assign that point?
If there's a point literally in between and the clusters won't stop moving, there's a stopping criteria. If the clusters won't stop moving, it's like chess. You ever played chess before? There's a rule in chess. If the opponents make the same move 3 times in a row, it's a stalemate. Same thing. If the clusters keep moving back and forth n times in a row, it stops, and then wherever it was last, it's just decided that way. So it'll just oscillate between the two. We'll talk about it after class, I promise you. But this number can be negative. This number can be negative. So what does the denominator do? The max of those two numbers, the bigger one. What does the denominator do?
Makes it a fraction.
Say it again?
Makes it a fraction.
It makes it a fraction, yes, but specifically, what kind of fraction?
It's much bigger.
Yes. Similar, negative 1 to 1. So without the denominator, this ranges from negative infinity to infinity, theoretically. But if you divide it by the bigger number, it always makes between negative 1 and 1. So the silhouette coefficient can take values between negative 1 and 1. By the way, if your silhouette coefficient is 0, that implies overlapping. If your silhouette coefficient is 0, there's this mix between cohesion and separation, and your clusters are overlapping. In general, we want separation to be high, cohesion to be low, which implies a silhouette coefficient of 1. A negative silhouette coefficient, in words, means the cluster radius is larger than the space between the clusters. And sometimes the clusters overlap in this case. So as an example, well, that's your example. I'll show you more after class, I promise you, but there's a lot to get through. Now, that's the silhouette coefficient for a single point. The silhouette coefficient for the entire graph, for a cluster, is just the average silhouette coefficient among all the points. Makes sense. Find the silhouette coefficient for all points and then take the average. That's the silhouette coefficient for the cluster. The overall silhouette coefficient is the average silhouette coefficient across all clusters. So for k clusters, add up all the silhouette coefficients and then divide by k.
Is the number of points
I'm sorry, mi is the number of points in the ith cluster. Yes. Cool. We're not going to be doing this by hand, don't worry. Scikit-learn does it for us. So that is our overall way of assessing clustering quality, silhouette coefficient. It's not the only way, but it is our first way of understanding how well our clustering is doing. A useful application of cluster validation is to determine the best number of clusters. So this actually becomes very important. So in our example today, we're going to look at songs from 6 of my Pandora stations. And the cluster analysis will tell me that I have to listen to 4 types of music, not 6. And it's going to tell me what they are. So how, it's pretty, so you can either compute the sum of squared errors, SSE. We've actually seen sum of squared errors before. Essentially, sum of squared errors is just you add up, same as before, add up all the errors between each point in its centroid, square them, and then take the square root. Sum of squared errors is the same thing as always, or the silhouette coefficient for each different values of k. We'll use, more often than not, the silhouette coefficient because it tends to yield better results in clustering. I do have examples of sum of squared errors. Ultimately, the whole point. These are all suggestive, which is not a fun thing to say in a machine learning class, right? It's all a suggestion. It's all like play it by ear. Because in unsupervised learning, that's all we can do. There's no question, there's no answer, there's no right, there's no wrong. Anything I say, anything you do in unsupervised learning must rely on human interpretation to be meaningful. Remember the Esri data, where there's 67 types of people based on census data? And then in this area, there are people who go to yoga and Pilates and go to... That was the cluster analysis. They made all these clusters of people based on demographic and shopping behavior, and then gave them names. The humans gave them the names, was it laptops and lattes or whatever. So it must rely on a human interpretation, because there's no question and answer. Almost done. Strength, k-means, is a super popular algorithm because it's efficiency and simple and intuitive nature. If anyone ever speaks to you about clustering in the real world, 90+% chance they're talking about a k-means algorithm. Very common in clustering techniques, very common. Weakness is very scale dependent, and it's not suitable for data with a widely varying shapes and densities. And I have examples of all of those with pictures. K-means clustering fails a lot. It fails a lot, particularly when your data are scaled weird or differently, or if the shape of the data is weird. And we're going to learn another machine learning model in here called support vector machines that actually deals with weirdly shaped data. But here we're going to see where k-means falls short when the data are shaped weird. All right, let's take a look. So I'm opening up our code base to the 10 k-means class exercise. So there's actually 5 scripts for today, and just to tell you what they all are. K-means class exercise is a quick intro to k-means to show you the syntax. Then I'm going to use the analyze Pandora, which will actually use our Pandora data set. After that, I'll talk about the validation, the silhouette coefficients. And then if I have time, I'll show you the limitations of k-means, which is like the weirdly shaped data. The 5th script is called Scrape Pandora. And what it is if you give it your Pandora string name and run the script, it will make a CSV just like the one I'm going to use, but of your own personal songs. So if you want to run today's work on your own personal Pandora list, you can run it through the Scrape Pandora script. All right, so I'm looking at 10 k-means class exercise, and I will do my imports. I'll import from scikit-learn.cluster import k-means. I will use matplotlib. I will import my data sets because we'll be working with our handy-dandy iris for our explanations, pandas, and numpy. So your first exercise of the day, I want you to take 5 minutes, 3 to 5 minutes to work on this. Don't scroll down because the answer is down there. Try to find the centroid of the following data. So I have 3 points. 2, 5, 4, 4, and 3, 3. Sure, you can do it by hand, but code a way to find the geometric center, the centroid, of each of these 3 points. So take 3 to 5 minutes, find the centroid of these points. All right. So what do we get? What's the centroid? What is it?
3, 4.
It is 3, 4. So for the x coordinates, 2 plus 4 plus 3.
So it's the same as sum b divided by length.
It's adding up all the x coordinates and dividing by the number of points they're on. So 2 plus 4 plus 3 is 9. 9 divided by 3 is 3. For the y coordinates, we got 5 plus 4 plus 3, which is 12, divided by 3 data points, which is 4. So the geometric mean is 3, 4. I used NumPy to get the answer. I took the mean along the axis 0, which are actually my columns. But you can have done it any way you want. All right, let's import some iris data. So we got iris equals datasets.load iris. Nothing is different here. We have this D, which is this NumPy array of data points. You now know every single row is a flower. We have sepal length, length, petal width. Everything is fine and dandy. I will go ahead and on lines 43 and 44, make a data frame out of it. So they're no longer a NumPy array, they're now a data frame. The data frame's column names, no surprise, are sepal length, petal width. Fair enough, nothing out of the ordinary. All right, I will set my NumPy random seed. Why am I setting my NumPy random seed? What does it do? What does it make sure we all get? Same random results. Why does that matter? In k-means particularly. What's random in k-means? The initial k. Scikit-learn chooses the random k metric. It will randomly put those k's wherever it wants. But if I set the random seed, they all get put in the same place for us. All right. I'm going to run k-means on my iris using 3 clusters. Note, what's the one thing I didn't import from data sets? I got all my sepal length, sepal width, petal width. What did I leave out? The species. The species. I'm sorry? This, what'd you say? The flower type, right?
Yeah, I said response.
Response, the response. The flower type. The species. That thing we used to care about predicting, I don't care right now. I am assuming I don't know what any of these flowers are, and I'm going to try to extract structure regardless. So to run a k-means, it's very similar to any other predictive model. Line 49, PST, I will instantiate, equals k-means. I have parameters. N clusters equals 3, and my init, my initial clusters, are going to be random. So I instantiate, and then I fit. And what is weird about this fit than the other fits we've seen before? est.fit D. What's different about this fit and other fits, Ozzy? As opposed to? So in the past, we would put 2 arguments, our predictors and our response. But there's no response. So the only thing we're putting into our k-means is this, all of the data. And then I predict, oops, I have to fit it first. And then I predict my data. Predict is a misnomer in my opinion. So whoever wrote scikit-learn, I think predict is the wrong word, I do. Because predict, what it does is it takes the data point and essentially just runs k-means cluster. And now it assigns to each one of them one of the clusters. So now, in lines 33 through 53 rather, through 57, I'm now going to plot it. This is what I get when I run k-means of 3 on Iris. This red, this yellow, this blue is not species. It's not. These are actual what the k-means clustering got. We're not assuming we know the flowers at all. But this is what the k-means clustering gives us. Now, if I want the actual clusters, there's a parameter called cluster centers. And those are our centroids. And they give you an xy or an xyz or however many dimensions. They give you a data point. And if you run lines 53 through 66, it'll put the clusters inside of the graph. So these black crosshairs are where the clusters actually are. All right. I want to take a brief tangent to talk about different ways of visualization. Because clustering provides this unique window of opportunity of how do we visualize data. So up till now, you've been very used to scatter plots, scatter matrices, line plots, things in 2 dimensions, right? With Iris even, how many dimensions do we have in Iris? 4. Sepal length, sepal width, petal length, petal width. This is a graph that plots petal length versus sepal length. That's it. So what is one way that we know to visualize a relationship between all 4 variables? Scatter plot, scatter matrix, right, between all 4. So I can use a scatter plot grid. So Pandas does come with one, right? In Pandas tools, we can do a scatter matrix. Yes, you can. There we go. Look how pretty that is, right? Using matplotlib, I can actually make it a little bit bigger and a little bit nicer. So, but with a lot more code. So in those 2 lines of code, I can produce a scatter matrix, and if you want to zoom in on your computer and take a look at it, you can. But however, from line 83 to 104, and yes, it is a lot of code, in matplotlib, I can make the same exact plot a little bit nicer with more color and a little bit space and things like that. So What we're looking at is all 3 clusters based on all 4 characteristics all plotted against each other, right? Well, here rather it's petal length, sepal length, all of them, petal width versus sepal width versus sepal length. Now, if you look at all of them at the same time, what do you notice about the clusters? Sometimes they're good, sometimes they're not so good. So when I do petal width versus sepal width on the bottom right, you'll see that the dots overlap, which is fine. It's fine. What does that mean by the silhouette coefficient, though? It's probably going to be negative. Could be negative. Depending on how much they overlap, silhouette coefficient could be negative. But this is really cumbersome. Now, some of you have been asking, hey, Sanan, how do I do a 3D plot? And I'm very against 3D plots. Very against 3D plots. Especially if you're going to present it to someone above you at your workplace. But here it is. So you can plot a 3D plot in Python, and I gave you the link to the example that I took it from. Ooh, yes, I know, it's nice. So you can plot a 3D plot, but I argue this is even worse than a scatter matrix. This, to me, is almost unreadable. Like, I have zero concept of depth in this graph, and I have no idea what I'm looking at. So I honestly argue that 3D plots are one of the worst ways to get your point across. Unless it's a super cool, interactive, zoom in, zoom out, like a really good one. Generally, by themselves, 3D plots are great. But there's a third option, and it's an option that I learned about in grad school when we were learned on how to conceptualize very large dimensions. Because one of the classes I took was, how many dimensions is the universe? So this is the thing that they showed us, and it's awesome. It's called parallel coordinates, and it is by far my favorite source of visualization, parallel coordinates. And without explaining what it is, I'm just going to show it to you. So before I plot this, I'm going to ask you all to please think of how you visualize points in space, 3D points, my fist is here, this table is here in 3D space. Forget that. Because this is what parallel coordinates look like, and they're awesome. So here's what we're looking at. Every data point is no longer a point in space, it's a line. And think about that line moving through the dimensions up and down. So every vertical line represents one of the 4 dimensions in iris. Sepal length, sepal width, petal width, in that order. So these lines are actually each flower moving through the dimensions. And they kind of become ribbons, almost, instead of data points. So in parallel coordinates is one of the best ways to conceptualize large dimensions of data. Arguably better than a scatter matrix. Although scatter matrices are great when you want to discern patterns between single variables. But in clustering, parallel coordinates becomes very important because when I'm clustering, I would see this red ribbon and see, wow, look how differently it moves through space, through dimensions, than these other ones. These blue and yellow have this very up and down, very jagged movement, whereas the red seems to move through the dimensions much differently. So parallel coordinates are actually a very nice visualization of higher dimensional data. And they're actually very easy to do in Python. It takes 2 lines of code. And it also comes out of pandas, so it's already built in. It's nice. Okay, so how do we determine the number of clusters? Obviously, for iris, I choose 3 because there are 3 types of flowers, and I knew that. But what if I didn't? What if I had no idea? What if I was just given flower data? What if I was just given all 4 of those dimensions and someone asked me, how many types of flowers are in this thing? Like, actually. That's a scientific question. No one came down and said, there are 10,000 animals in the world. Go, find them. That's not what happened. We're just trying to figure out what makes this spider similar to this spider, like, but just different enough that they're different species. So we have to figure out how many Ks there are. So to do that very easily, I'll create a range between 1 and 15. Note I'm including even numbers. This is not K and N. I'm not worried about ties so much. For each K range, I fit a K-means with that many clusters. So I'm going to fit 15 different K-means from 1 to 15. So the first thing I'm going to do is I'm going to calculate my silhouette coefficient for each one, which recalls a number between -1 and 1. So I will have my silhouette scores. Note I can define my metric. I can define my metric as Euclidean, which I will do for all of my silhouette coefficients. I will make my silhouette scores, and I have 15 silhouette scores, all between -1 and 1. I'll use matplotlib to plot them. And also I'm going to mark one of the points. So what we're looking at is as we add the number to k, i.e. we're adding complexity to our model, this is the same concept in predictive and not predictive. As I add complexity to my clustering algorithm, note my silhouette coefficient plummet. As I add more clusters, the data are becoming less and less clusterable. So really, what I'm looking at is I want to maximize my silhouette coefficient. I want a silhouette coefficient that's close to 1. And I also want to minimize k as much as I can. Now, why is 3 circled and not 2? Because why wouldn't 2 be circled? Because 2 has a much higher silhouette coefficient and it's smaller than 3. Why would I choose 3? Well, here's the part where it relies on human interpretation. Because I'm not saying it because I know there's 3 flowers, but there's something called the elbow method. The elbow method, and I'm putting it in quotes because you're not going to find it, named in very scientific books. The elbow method essentially says, pick the number of k where that's on the elbow of the graph. Because more often than not, when you graph your silhouette coefficient or your sum of squared errors, which I'm about to do, you see this elbow. I.e. it plummets, and then after a while it is kind of like a bent arm. So what it's usually saying is, on the first elbow, choose the point where it starts to slow down. The reason being, if you just choose 2, well, I'll show you. If you just choose 2, look at our clusters. What would the 2 clusters be? It would be these red points and maybe some of these, and then the rest of them. So if you choose 3, though, while the silhouette coefficient does go down, what starts to happen is the silhouette coefficient goes down, but it's starting to level off, i.e. it's starting to stabilize. So this becomes a question of variance. This becomes a question of, I could choose the k that's smaller with a higher silhouette coefficient, or I could choose one more with a lower silhouette coefficient, but it comes at a point where the silhouette coefficient is start to level off and become more stable. So I'll get to you in a second time. So which one's better? Not up to me. It is not up to me to decide if 3 is better than 2. I decided that because I generally follow the elbow method. It is up to you to decide which is better. Are there only 2 types of flower? Or 3? Or 4? That's up to the data scientist. But general practice in data science is that using the elbow method, you would generally pick 3. That's all I would say. Sorry, yes.
Would 6 be another elbow point?
Yes, and the elbow method says pick the first one. So of many elbows, you generally pick the first elbow because that minimizes K. But yes, this would be another elbow point.
So
Correct.
steep decline and then level.
Where it starts to level off, yeah. So again, not up to me to decide that 3 is better than 2 or 3 is better than 4. But it is general practice in the elbow method to say 3. Option 2, you can minimize the sum of squared errors, otherwise known as inertia. So the within sum of squared errors on sum of squares is just, again, the addition of the distance between the point and the centroids all added up squared. So this is essentially penalizing the outliers. So this one is penalizing outliers. And if you do this, it's actually much clearer. Looking at both graphs, the within sum of squared errors, sorry, I keep saying that. Within sum of squares, there's a much more definite elbow. There's a large single elbow, and this is definitely clearly telling me 3. Because 3 is where it starts to level off. So between both sum of squares and silhouette coefficient, between both of them, I would choose 3 as the number of flowers that exist in my clusters. Yes?
So is there a general wisdom of use the first method, second method, both methods?
Both.
Converge? Okay.
Generally both. If they're competing with each other, generally silhouette coefficient. But if they both, like for example, we could argue this graph, but when it comes to both of them together, okay, now that it was between 2, 3, and 4, but this is definitely saying 3, I would choose 3. But if the silhouette coefficient looked like this, and the sum of squared is more jagged like this, I would choose silhouette coefficient over sum of squared. So that's a basic intro into the kmeans clustering. Let's take a break, 10 minutes, come back, and we'll do it again with a larger data set of Pandora sums. Pause this. Go. All right, welcome back. Hope you had a good break.
Yes, yes.
So, are there any questions up till now about the basics of kmeans, how it works, why we do it? Fair enough. I'll ask you a question then. Now, I mentioned before that a k-means, or clustering in general, can be a very good precursor step to a supervised learning problem. Can any of you think of a situation where that might be the case? Can you think of a time where you have data and you would use an unsupervised learning model first before turning to a supervised learning method? In what situations? Yes?
Exploratory data analysis. Just exploring a data set. Like sector clustering to patterns.
Yeah, you could argue that as a part of exploratory data analysis, clustering would be a type of exploration. You're trying to explore patterns. You're trying to explore clusters. What makes them similar? What else?
If you're able to convert a linear regression problem to a logistic regression problem, you're trying to figure out how to group the response into those categories.
So to turn regression into classification, right? That could be one reason, yeah. What if I didn't know the response? Like not even pretending to not know it. What if I literally had none? Could I use clustering to come up with a response? Give me an example. Yeah.
Yeah, you could like this data set, the average data set, you could find a cluster
So you're saying find the clusters and then use the clusters as their response. And exactly. So in one of the last classes, in the last class, one of the students took bowling data from semi-pro bowlers and of all the predictors of all the scores they got, and he did it all with clustering, and he solved all the different clusters, and then he made the categories great bowler, good bowler, mediocre bowler, poor bowler. And he did that by looking at the clusters and saying, this is definitely what it's telling me. And then after that, he made a predictive model to predict new people coming in. So you can use unsupervised clustering to create responses that did not exist before at all. Another example could be music, which leads us into the Pandora dataset. So, using my scraped Pandora script, I used my own screen name, and I got a bunch of songs that I like. Now, if you look at my Pandora, and if you're unfamiliar with how Pandora works, I will describe it very quickly. You can create a station based on a type of music you like, and then you train it to say, I like this, I don't like this, and then it learns from that and it gives you more things like it. Now, we do have an entire day where we essentially rebuild Pandora from scratch, but today is a precursor to that. Today we're understanding how the songs are grouped together in the first place, so we can even make a prediction. And then we'll build upon that to actually make a recommendation. So, I have 6 stations. When I scraped my Pandora, all of my songs, I have 6 stations. And please don't make fun of me, and I haven't changed these since literally high school. Teen Angst is one of them. The Wombats, which is a band. Meek Mill, which is more aggressive rap. Electronic, international, different languages. And sleep, something to fall asleep to. So I have 6 stations in my mind. Now, every song has features about it. Fast song, slow song, in English, not in English. Use of certain instruments. Now, Pandora has tens of thousands of predictors for each song. And they're actually all assigned by humans. Humans actually sit down and they write down things about the song. It's a job people have, is to write down qualities about song. Now, we actually get some of them. If you click on a song in Pandora, fun fact, if you've ever done this, you probably never have, if you actually click on the song, it actually shows you some of the features that it uses to make its prediction. So for example, the song I was just listening to has house roots, 4 on the floor beats, electronica, catchy, beats made for dancing, female vocal, clear pronunciation, I don't know, radio-friendly stylings. They get weird and specific really fast. And each of these songs has a list of these. Yes?
Is there a way to wait? I care about this.
The question is there a way to weight a feature, like make something matter more than something else? Yes, there are many ways of doing it. I don't do it today, but an easy way to do it is to double count that data point. Essentially take the data point and just put it in the data set again. So if I like this data point, I want this data point to count for twice as much, put it again in the data set. If you want a column to count for more, like if you happen to want house roots to count for more, you could literally double that column. So there are ways of doing it, and I'll do it in this class, and I talk about it throughout, but I don't. Yes, to answer your question, yes. You can weight classes and weight data points more than other data points. So here are some of the features, but there's hundreds. Did they say hundreds? There are thousands, and I've seen there are thousands of predictors that they use. But each of my songs, I grabbed the 20, 25 odd predictors of each one, and I created a data frame out of it. And it looks like this. So if I do df.head, you'll find that of the first 5 rows, I have 314 columns. Excuse me. Each row represents a song. Each column represents some feature. So for example, the first song is called "The First Bass is the Deepest," which is an electronic dubstep song. So if you look at the first row of "The First Bass is the Deepest," its folk influences is false. There's no folk influences. Indian influences, false. Use of ambient synths, false. Sexist lyrics, false. Good, I guess. I get like nervous, but the fact it's even in there, I get nervous. And if you go down, every single one of these columns is true or false, telling me if that particular feature resides in that song. So I have 314. So for those of you who work with the ingredients data set, very similar. Each row represents an ingredient, a recipe, and each column represents an ingredient in that recipe. And true if the ingredient belongs in the recipe, false otherwise. This is just songs and characteristics. And some of the features are really weird, like cash-obsessed lyrics. Jazz, techno, ska influence. So they get really specific really fast. But this is my data set. This is an actual data set pulled from the Pandora databases. This is what I like. Now, I have 6 Pandora stations. Let's see if the math agrees. So, I have 314 columns, except for the name of the song. So, quick exercise for you guys. Take 3 to 5 minutes. If you scroll down, you'll see the answer, but try it yourself first. How many songs do I like that have Indian influences? Take 3 to 5 minutes, work by yourself with the person next to you. Find out how many songs I like with Indian influences. Bold. Yeah, I know. Bold. Okay with it.
I'm bringing my own, but usernames. It's just for email.
Good question. No.
Oh.
It's not. It's in your, when you go to your Pandora, when you go to like settings. Actually, let me show you. I'll just do it up here. I believe. Where is it? Maybe. Yes. If you go on Pandora, if you want to get your own, if you go on Pandora and go to My Profile, this right here is your username. Mine's sanan.u.algebra. So if you do want to do this yourself later on, I suggest, because it'll take about 10 to 20 minutes to scrape, especially if you have hundreds of songs. If you type in this username into that script, you'll get your own data set for your own songs that looks like this one for mine. So this is an FYI. But be warned, you must set, oh my gosh. Your settings, you must have public listening activity for this to work. Because if it's private, you can't scrape it. If it's public, you can't. So if you want to change it, you have a question?
Assigns
Great question. Who assigns catchy hooks? Humans. At Pandora, they employ hundreds of humans who have degrees in music or whatever, and their job is, when the new Justin Bieber album comes out, their job is to listen to that Justin Bieber album 100 times, and then for each one, write down catchy, I guess, true. Use of female vocals, 100%. I bash on Justin Bieber every single class. I really apologize. I'm going to get sued or something. Bring it. So, how many songs with Indian influences do I like? df indianinfluences.sum. Uno. Now, I'm really nervous to do this. Trust me, I am. I wonder, what is it, cash-obsessed lyrics? Oh dear. 5. I enjoy 5 songs with cash-obsessed lyrics.
Do you have cues that are sexist?
I don't want to do that. I don't want to do that. Because sometimes my girlfriend watches these videos and she'll get mad. And then I'll try one more, house roots. All right. I enjoy a lot of songs with house roots. which is essentially one of the bases for electronic music, which makes sense because one of my stations is dubstep. So already we're learning a lot about Sanan. That's fine. Let me turn this back to Indian influences. So let's start with a cluster of 4. Because sure, I have 6 Pandora stations, but I don't know how many are, actually mathematically viable, how many types of songs I actually like. So let's figure that out. So let's start with 4. So I will instantiate. Question?
Sorry, quick question.
Yes.
How do you graph your own data?
It's actually not that after it's with the URL. So it's not that, it's that.
Oh, yours is different.
Yeah, same as mine.
Right.
You can edit that.
All right, Angel Games.
Yeah,
I thought that was
My
embarrassing.
AI is
Fair enough. So it's been brought to my attention that not everyone has their username up here. I did not know that. I'm told literally right now. However, it is always, if you click on my profile, in the URL. So you can always go to the URL, pandora.com/profile/ what's your screen name again? What's the number?
375.
So I wonder if I can do this now.
Oh, scrapers,
There we go. So you can actually go to, so if yours is, because your profile is public, I am able to take your song preferences. So this will work with any screen name, whether or not you own it or not. Just FYI. Sorry. I didn't mean to. If it makes you feel better, mine was Wave Titan 53 in AIM screen name. So if it makes you feel better. So let's start with 4 clusters. I will instantiate kmeans with 4 clusters. Song cluster equals kmeans, n clusters equals 4, and init equals random. I will fit my data frame minus the name. So all this is data frame, getting rid of the name column, the name of the actual song. I don't care about the name, I only care about the other 313 predictors. And then I will predict them. And again, predict is a misnomer. Because predict, all it's doing is assigning each point to a centroid. One of the 4 centroids. And now what this for loop is going to do is I'm going to get the cluster centers. And then I'm going to use NumPy to actually figure out which songs are in each cluster. And then I'm going to actually show the centroid of each cluster. And it will look something like this. This is what happens when I run 4 clusters on my songs. And again, kmeans, well, 98% of the time, always converge, even if it's not the perfect number of clusters. So we'll take this with a grain of salt. So if I try 4 clusters, the math says these are the 4 types of songs that you like, Sanan. This first one has beats made for dancing. Pretty good. Effective synths, synth swoop, modal harmonies, size, highly synthetic sonority. What does that sound like? Sounds electronic. Synths, right? Dancing, electronic music. Sounds like my electronic playlist. Let's look at the second one. Modal harmonies, prevalent use of groove, chordal patterning, house roots, a variety of synth sounds. That kind of sounds like electronic, but not so much. Because when I hear use of groove, modal harmonies, chordal patterning, that sounds more like rock music. This sounds more like a rock station. Next, vamping, electric rock, repetitive melodic, acoustic rhythm guitars. That's definitely like a rock station, right? And then last, electronica, consistent rhyme, syncopated beats, hardcore rap influence, and use of chordal patterning. What is that? That's my rap preference. So far, it's actually not doing a terrible job at telling me the 4 types of music that I like. But is 4 the right number? That's really the question here. Is 4 the right number? Do I actually like 4 types of songs, less or more? So Our silhouette score for 4 clusters is 0.2. Not great if you think about it between -1 and 1, right? It sounds like a not so great metric. But those of you, so I already referenced the ingredients people, who worked on the crime data and on Wednesday's class, who did crime data? Be proud. Be proud of who you are. Now tell me you didn't go home and then use your newfound knowledge to commit crimes. No. So what was the hard part about your data set that I mentioned? Predicting human behavior sucks. What is Pandora, if not my own behavior? Pandora, sure, the songs are quantified by musicians, whatever, but in the end, who decides if it's good or bad? Me. I am the person who gets to reap judgment on my songs when I say thumb up or thumb down, like, dislike. And that's very much based on my mood, which is human behavior. So Pandora classification or clustering is affected by human behavior, i.e. whoever the listener is. So 0.2 might not be so bad. To know, we should compare it against other values of k. So I will try between 1 and 15 k's. 1 meaning I only like one type of song, or I like 15 types of songs. Similar to the iris, I will run a kmeans for each one. Note it takes a little bit longer than the iris data set because I'm going through much more songs than I am 150 flowers. I calculate a silhouette score for each one. And this is my result. This is an interesting graph. I see a weird elbow, but it's not a perfect elbow. Fine, fair enough. So in my silhouette score, I see with 2 songs, I actually have a, with 2 clusters, I have a silhouette score of 0.2. With 3 clusters, I have a silhouette score of 0.22, and then it kind of plummets. Right? So I circled the 4, because technically to the elbow method, I should choose that one. But here's your chance to disagree with me. I'm only circling the point which the elbow method would choose. Do we think, as humans and data scientists, that 4 is the best number? No, why not?
It seems like 3 might be a better choice because it has a higher silhouette score. And 4.
No, yes, I mean, what is it?
It just doesn't feel good.
It doesn't feel good, right? Why doesn't it feel good? Why can we quantify that? So in the elbow method I claimed before, you want to pick the point where it starts to stabilize, right? Well, not only is it starting to stabilize, this is pretty much the stabilization point. Because before it was very high, and then all of a sudden it's stuck down here. So it's a really weird, like, crooked elbow. Kind of weird elbow. So while I've circled 4 clusters by the elbow method, I personally am inclined to believe that it could be 3. But whether it's 3 or 4 is irrelevant. Because what is it not, definitely? 6. Which is the number of stations that I have on Pandora. So whether it's 3 or 4, we can argue or agree, it doesn't even matter. The interesting thing to me, at least, is when I made 6 Pandora, and I take Pandora very seriously. When I'm like liking and disliking songs, the clustering is telling me you only really like 3 or 4 types. You're just kind of spacing them out among 6 stations. Now, in songs, fine is not the most conclusive, like, oh my god, in the New York Times. But when might this be really interesting and useful? When might we be very flabbergasted? Yes, I said it. When there are less clusters than we think there are on something. Really?
Marketing. You think you have 6
It's a big one. If you're a marketing company or you're doing marketing for any company, and you say, okay, we have 6 demographics. We got young millennials, we got in college, we got right out of college, and we got all this. And then your data science guy comes in and says, actually, you're right out of college and you're in college are pretty much the same person. So you really don't have to differentiate. We just consolidate the budget and save money there. So that is an actual real example of being happy that there are less clusters. What if there were more clusters? What's an example where it would be really interesting if you had more clusters rather than less? When would you be surprised to know there's more of something than you originally thought?
I just think about that medical example with the kmeans. So you're trying to find reasons for it was your example.
The neonatal infection?
Something like that. Yeah, you would find more reasons why neonatal infections happen.
Fair enough. Yeah, so the neonatal examples, or the neonatal example, if you do a clustering of all the different predictors, you might find different types of infected children. So if I have 15 different predictors and I originally think, well, they either have it or they don't, there could be a third. There could be they have it, but they're really not displaying the qualities of it, so I don't know what to do with it. So your clustering might tell you that there's a third option that didn't exist between not having it and having it. So the clustering is actually a very interesting way to tell us things we would never have gotten before. So for those of you who actually actively use Pandora, I know some people who have like 30 Pandora stations. Try it yourself, and it could be a lot of fun, personally. All right, so that's the end of me using kmeans to actually do unsupervised learning. The remainder of today's class, I'm going to be showing you some more graphs on when kmeans actually fails on weird data sets, and also on cluster validation using sum of squared and silhouette coefficients. Yes?
I thought you mentioned earlier that kmeans can end up at different points depending on the randomly chosen initial starting points.
Correct.
So I'm surprised we don't cycle through a bunch of different random starting points. So if you run this again, you'll end up in a very different looking chart based on the random initial starting point.
If you run the 4 clusters again, you mean?
Yeah, start at est. Yes.
Est? Oh, you mean down here?
Yeah. Like the chart looks like if you run it a few times, you end up in a different chart.
Sure. Hold on. Here it comes. Right? This is a different chart. You
For
can.
example, like mine has 4 at like 0.2.
Yes. Yours 4 is at.
Is that 0.2 instead of 0.04.
Yeah, I don't know.
So it's like way higher.
Oh, okay, yeah.
Much better choice.
So, because the initials are random, this graph is going to be random each time you do it. Correct. So, if I run it again, and if you actually recall before, when I did the silhouette score, I said 0.2. And then when I did the graph, it was 0.04 or 0.06 or whatever.
Yeah.
See, here we go. See, here, I ran it again, and because of the random initialization of the k's, 4 actually becomes a fairly good one, which is where the argument comes in as, is it 3 or 4? Even the random k is having trouble deciding if it should be 3 or 4.
Wouldn't that be 6?
In this example, the elbow method would be, actually it would be 5. Here's where the elbow is. It's, again, everything I'm saying is suggestive, especially in an unsupervised learning model. Everything I say is suggestive. There is no answer. I cannot tell you you're right or wrong because A, it's random, the random coefficients, and B, unsupervised learning is highly reliant on human interpretation. I will interpret that 3 or 4 is best. Now, by the elbow method in this graph, it would be 5, maybe 6. But if you run this graph several times, you would essentially come to the conclusion that it is probably between 3 and 4 that you get your best result. But again, I cannot speak to which is better because I'm not allowed to because there's no answer. And that's just something that we have to live with. Yes?
And then the other question was, I was thinking k-means wouldn't work well on high-dimensional data sets because it's linear distance. And this seems like a high-dimensional data set compared to
It works fine on high-dimensional data. Where it starts to fall apart is if you have high-dimensional data, which are all scaled differently. Yeah. So these are all scaled the same to 1 and 0. Yeah. They're all in the hypercube.
So I think actually this is part of his original question. Why don't we run the k-means like a couple of times and then take the average?
Sure.
Wouldn't that be safer?
Yeah, and that's essentially an extension of cross-validation. It runs everybody running it 5 times. Yeah, that is an extremely acceptable validation. I just happen to not know this code base. But yeah, that's a very fair way to assess it. So essentially what I'm doing now, but more programmatically, just keep running the same k-means from 1 to 15 over and over again. Or run 1k 10 times and average it. Or run 2 10 times and average it. Because you do get this interesting graph. Yes?
Well, we go over how to normalize the data such that each dimension has what's considered an appropriate weight. Because you're saying like if some dimensions are much longer than others, then it can really skew the data.
Yeah.
Do we go over ways to kind of look at those dimensions?
Yes. So the question is, are we going to go over ways? So I said different scales are bad. Are we going to go over ways on how to scale the data? Yes. There's not a day where we do that, but I'll start from now on. I'll start to do it while I do the code, just so you can see like, oh, this data is scaled wrong, and you'll see me do that. But for now, I'm showing you the limitations on when it's not scaled properly, so that you understand why it's even useful to scale the data. What's the question? Yeah.
There are ways, there is other methods very similar to k-means based on that. They don't have to decide on k, which is something like hierarchical clustering. K-means can just check that out. Just learning more about this.
So Sri's mentioning another type of clustering called hierarchical, where you don't have to initialize a k or a set number. And yes, there are hundreds of types of clustering in the world. Kmeans is but one of them. And there are many other ones. In fact, in the resources, in one of the resources, I do talk about, I don't, but someone else talks about a different clustering technique that you can look at as well. All right, so moving on. That's Pandora. So when it comes to cluster validation, so this code base is extremely dense, and it is mostly pictures, which is very contradictory and funny. It's very dense, but it's only very dense to make very clean pictures. And I use a lot of very fun data generators, for example, make blobs. So scikit-learn comes with pre-built functions to make shapes of data for teaching purposes. So what I'm going to do in this code base is kind of show you the visualizations of within sum of squares and silhouette coefficients. So this first block of code is generating dummy data for k equals 2. So here we're looking at a data set which I made 2 blobs, which I literally use the function make blobs. I made 2 blobs of data, and I labeled them the color that they are supposed to be. So this is the data we're going to be working with for the next couple minutes. So one is yellow, one is red, quite obvious. Now, if I look at the silhouette scores for this data, which is clearly supposed to be 2 clusters, and then I run a k-means from 1 to 15 on that data set, it takes a second, so you get a model, there we go. This is what it looks like. So, not to our surprise, when I have cluster 2, I get a silhouette coefficient of 0.85. Which is actually funny, because why isn't it 1? You would think that with a data set, come on, that perfect, you would think your silhouette score should be 1 when you have 2 clusters. And let's try running it again, right? Because the random coefficients, let's try it again. So I'll run it again with new randomly initiated k's for our k-means. And this time we'll see what happens with 2. So run second, run second, run second. Look at that, it's still 0.85, pretty much the exact same. How does that happen? Look at 3. 3 is about 0.58. What would 3 look like in this blob data? Where would that third cluster be? Kind of be like right here in the middle, right? Right here in the middle, and then we kind of grab the outskirts of these yellow, the outskirts of these red, and call that a cluster. And then you have yellow push back and red push back. But why would 2 clusters? You look like you have an answer. Oh, sorry. So why do you think that 2 clusters would end up having a silhouette coefficient of 0.85? Why not 1? What are the 2 things that make up silhouette coefficient? Yeah. Mm-hmm. All right, I'm going to try that again with the equation on the board. So here's the silhouette coefficient equation, right? So why isn't it 1 in this case? Well, we have average between cluster minus average in cluster divided by whichever's bigger. So if this were 1, then that would mean AI should be close to 0, right? Is it? No. For the silhouette score to be 1, it requires that AI be really, really close to 0. If AI, I'll go back to it, if AI is really close to 0, the average in-cluster distance is close to 0, that means all of the points in the yellow and the red clusters should all be like fighting for the same space, but they're not. So the reason the silhouette coefficient is not 1 is because the cohesion, the in-cluster distance, isn't 0. The cohesion is still not amazing. There's still this straggling yellow dot out here, these red dots over here forming their own little like Zimbabwe of a cluster over here kind of thing. So it's not a perfect cluster, like perfect in the sense that cohesion is not 0. All these points are still, they're clustered together, they're far away from the red, the separation is very good, but the cohesion isn't perfect. So which is why the silhouette coefficient is not 1. It's because the cohesion is not 0. So if I calculate the within sum of squared errors, I get something that looks like this. Again, we want to minimize within sum of squares. So with 1 cluster, it's really bad. As soon as I get 2 clusters, my within sum of squared errors plummets. So by my elbow method, it looks like I would choose kind of a 2 right here. So these 2 graphs are telling me that 2 is a good number of clusters, which seemed obvious because we looked at the graph, but here's how we would actually use the graphs, the silhouette coefficient, and the sum of squared errors to figure that out without having a graph. All right, what if k were 3? Here are 3 blobs. Again, a lot of code just to make this. Just to make this graph is a lot of code. So now we have, and again, these are randomly generated blobs of data. But I made them so these are touching almost. These blobs are very close to each other. They're still blobs. You can clearly tell separation between the yellow and the blue, but there's like, it's ambiguous. And then there's this red guy over here who's just chilling. It's like Iris. If you recall the Iris data set, kind of looks like the iris data set. With two clusters close to each other, and then there's a red iris over here that's far away. So, if we look at our silhouette scores for a k-means cluster with 3 clusters, we get something that looks like this. Like this. Like this. Like this. So you can see a clear spike at 3 clusters. The k-means is telling me, yeah, there's definitely a big spike at 3. Now, I've circled 3, but the elbow method would disagree. The elbow method would say, maybe 5, 4 or 5. Which is interesting. This is really interesting, because if you look at the blobs, it's pretty clearly 3 clusters, but arguably, if a data scientist were in the room, they'd say, well, yes, I see that spike, but according to the elbow method, you want to choose where it's starting to stabilize, you choose 5 clusters. But this is the point I'm bringing up, is because it's standard practice to go by the elbow method, but it's clearly wrong in this case to go by the elbow method. But how do we know? How would we know? Obviously, we're looking at the graph, it's easy to tell, but how could we know without it? If the silhouette scores are ever very ambiguous, you have more questions, plot the within sum of squared errors. It generally clears things up. Because this graph tends to be much more definite in what it's saying. And here, our elbow method and our within sum of squares generally fails us much less in our within sum of squares. So our elbow method is telling us 3, and there's where I would agree. So our silhouette score is telling me, it's giving me mixed signals. My within sum of squared errors, however, not so much. Which actually is a very interesting side note. I'll talk about bias and variance in terms of models, but you could also argue there's a type of bias and variance for metrics. So in these metrics, your silhouette coefficient has a lower bias, but a higher variance. And it's weird to say it like that. But what I mean is, if your silhouette coefficient is behaving, it's generally the best tell how well your clustering is doing. The problem, as you can tell, and we saw earlier, if I keep running silhouette coefficient on the random k-means, it keeps kind of jumping around. Whereas within sum of squared errors, I'll run it again, doesn't really do that. It's a very low variance, quote unquote, metric. It doesn't change even if I have randomly generated k-means. 5. Again, a lot of code just for this. So yeah, it's running out of colors. It's like, I don't know, really dark purple and vaguely gray. So now I have 5 blobs. Let's see if our k-means is telling us the same thing this time. So I run k-means with 5 clusters, 15 times. Or I'm sorry, I run it for 5 clusters. Takes a second. Here it is. Now, what's wrong with you guys? There you go. Probably not big colors, but it'll take a second. Here we go. That's interesting. So now I have this TP graph. Whereas I add complexity, as I add k, clearly 2, 3, 4, 5 is at its peak, and then it plummets. And the elbow method guy is like, well, unless you're talking about someone at, a sideshow with a deformed arm, I don't really know where the elbow is. Because you could argue the elbow is around an 8 or 9. You could argue around here, 8 or 9, if you want to take it in its most pure form, but it's weird. It's telling us something weird. So for that, I turn to the within sum of squared, which generally gives me a much more definite answer. So my within sum of squares clears up the picture as a whole and is telling me, okay, definitely at 5 is when I hit my min for my within sum of squares without adding too many k's. Cool. Okay, good. So, any questions on that? And I'll do one more thing before I let you play around with the code for the last 30 minutes and ask questions if you'd like. Limitations. Now, while kmeans is great, and you should definitely try to use kmeans as part of your project if it's feasible, it fails sometimes. It fails, for example, I'll set my random C to 0 just to be safe. I'm going to make up some data here. You already see where this is going. Now, if I have data on different varying scales, so I have this very long, but not very tall data in my 2 dimensions. So it's weirdly shaped. It's an oval, essentially, if you want to think of it like that. This is the true data, quote unquote. I made it up, but these are supposed to be red, these are supposed to be blue, these are supposed to be yellow. Think of it like a setosa. These are setosas, virginicas, and versicolors, and flowers. These are true. Now, if I forget the species and I run the kmeans clustering with 3 clusters, this is what I would get. Uh-oh. What happened? What does it look like? Each cluster is a what? Forms a what? It's a circle. Each cluster is forming a perfect circle around it, and you can tell based on which points are colored in. So when you have data on differently varying axes, differently varying scales, kmeans clustering does a lot worse. Because if they're not on the same scale, this happens. Non-spherical shapes. So there's something called kmeans. Here's my original data. Pretty. It's supposed to be red, it's supposed to be yellow. If I forget the color and try kmeans, what do you think is going to happen? Circles, like this. It converged. The clusters definitely converged to 2 clusters, and it thinks it's totally right. The problem is, and it's not wrong, this yellow point is very close to this yellow centroid. In fact, it's the closest point to the centroid. There's no doubt in the kmeans' mind that this is correct. The problem is, this is a different type of similarity. Euclidean distance is not cutting it. And in a couple classes from now, we'll learn something called support vector machines, which tries to remedy this. In fact, it does remedy this by injecting dimensions into your data. It'll actually add synthetic dimensions to prevent against this. It will take these points on this moon and thrust it into a new dimension that it creates in order to get it away from this cluster. But this is where kmeans fails on its own. It doesn't recognize these interesting patterns. It only understands Euclidean distance. Yeah.
How can we detect this? If it's not 2-dimensional, how do we realize that it's talking about this?
There are a lot of ways of figuring that out. The easiest way, which is the most manual way, and it's unsupervised learning, the most manual way is if you think it's messing up, is you would take a random sample of your data points and see if they make sense. That is the most manual way. Because here's the problem with your metrics. Your silhouette coefficient, while it will tell you that there are a lot of points far away, it'll tell you that they're not very cohesive and they're not very separated, right? Because these points are very close to this cluster. So your silhouette score is your first your point of barrier, where it says, okay, my silhouette metric is not very good, and visually it's because this cluster is literally touching the other cluster, and the points within the yellow and red are not close to each other. So that's your first hint that something's wrong. But to really identify what's going wrong, you would have to like take a random sample of the points and look at them. That's kind of the inherent problem with unsupervised learning, is that without a question response, you have to go in manually and look at it. Last but not least, clusters of different sizes. These are the true values. You have a large yellow cluster, small red, small blue, and they're arranged like this. If I run the k-means with 3 clusters, here's what I get. The yellow, not so bad. It got a good amount of those yellows. The blue and the red, though, because they're clusters of different sizes, each cluster, each centroid, is essentially battling one another for space. Because it doesn't think that one centroid deserves more points than the other. It doesn't know that. All it knows is Euclidean distance again. So this blue centroid is saying, give me some of these yellow dots on the right. This red centroid is saying, give me some of these yellow points on the left. And then what happens is the yellow centroid loses out on some of its true points. Okay. That was a lot, I'm aware. And I asked you to take a journey with me into theoretical concepts that you could argue should not exist. But I do want to reiterate the main points of today's class before I let you kind of do work on your projects, because I'm going to get into the project milestone in a second, which is due in a week. Clustering, not only just one of the 4 types of machine learning that we're going to cover in this class, the non-supervised model, it is a widely popular subject when it comes time for, I don't know what my data is, I don't know what I'm doing with my data, I don't even have a question for my data, I don't know what to do. Clustering becomes a very effective tool when you are asking yourselves these questions. This data set is interesting, but I don't know what to do with it. I don't really have a question. I just want to learn more about it. Try a k-means cluster. See if you can find, there are like 3 types of countries in the world, for example. In one of our classes in BC, one of the students took adoption ratings for each country and used k-means to say, there's 3 types of countries in terms of adoption. Those who are very accepting, not accepting, and right there in the middle. And then he used that data, the clustering, the 3 categories, to make a predictive model. So when someone comes in with these characteristics of how accepting of adoption are they going to be. So clustering can actually be a very good segue into a predictive model. Even if you don't have a response at all, you can create a response with the clustering. Now, that was a lot. Again, I'm aware, and thank you for taking that journey with me. Are there any questions before I talk about your projects? The milestones that are due in a week. They're all just like, stop. That's fair. That's fair. That's why I had you fill those out before class started. Just kidding. So, next time on Wednesday, we will be starting natural language processing. I say starting because natural language processing is a 2-day endeavor. Wednesday is a crash course on all things sentiment. We will be taking a crash course into sentiment analysis, positive and negativity, how to detect subjectivity if something is an opinion versus something is a fact, how to pull out proper nouns and places and people's names out of large bodies of text. And we'll talk about an unsupervised way of clustering articles into topics. So we'll take articles and we'll actually classify those articles into types of articles, foreign policy, for news. To do that, there are some steps, because it requires some packages that do not come with content. Specifically, NLTK comes with Anaconda, but what you have to do is essentially download all of the packages for NLTK. NLTK, the Natural Language Toolkit, comes with about 150 to 200 megabytes worth of text data, which is not automatic. You have to tell it that you want it. So to do that, you go into a Python console and type import NLTK, like it's Python, and NLTK.download, and then a message box will pop up saying, do you want to download? And you say yes. I highly recommend, please, you do this at home before you come into class, because when 30 of you try to download 200 megabytes of stuff all at once, things go bad. And then 2 new packages, TextBlob and LDA. TextBlob is what we're going to use to do sentiment analysis. So positive, negative, how to determine what is a positive and negative sentiment. And LDA, which stands for latent Dirichlet allocation, which is an unsupervised method for classifying topics of text. So given just words, can you classify those words into generalized topics and then predict a new article coming in, what topic it is. As far as resources, the scikit-learn website has a really nice section on clustering, and they use kmeans obviously for most of their examples, but it's about clustering in general, and they give a lot of different definitions and pictures and fun stuff. And then there is a PDF here, which is a much more in-depth introduction to clustering with a lot more academic feel, if that's what you're into. And here they actually talk about what Sri was talking about, hierarchical clustering. So they talk about a lot more than just k-means. And look at all these pretty pictures. And next week, on Monday, you have a project milestone due. So the last homework, you were asked to hand in like a one-pager, which pretty much turned into a one-paragrapher. For some of you, it was a two-sentencer. That's fine. Your second milestone, I would like it to be much more in-depth. A minimum one-pager. Your second project milestone is essentially, I have my idea, I have some data, and I've also written some code to start to explore that data. So more often than not, students hand in a couple paragraphs talking about the problem, the data, where they got the data from, what they've already done with the data, and describing what they plan on doing. I want to study adoption rates in countries because I was adopted and I'm curious. I got the data from the World Adoption Center. I've already started to do a group by and pandas and all this, and means and sums. Here's my code attached in a .py file. The most interesting I've seen so far is that countries in Europe are much less willing to adopt than I thought previously. Something like that. Just to show to us that you have an idea, you're working on an idea, and you have at least one insight. And the milestone directions are always in the project.md file where it shows you the directions. All right. For the next half an hour, I would like you to work on your project because it is due, a milestone is due in a week. So I would really love it if for the next half an hour, you either keep working or start to work on your project. And while you have all the TAs and instructors in the room, please ask us questions to make sure that you are on the right track and you have all the data that you need to continue on. Because, spoiler alert, we're all pretty much, we're going to be on at the end of Wednesday, halfway through the course. So once we're halfway through the course, you really should be working on your project full steam ahead to make it as good as possible. All right, one last thing. Sorry, I am told that there are 6 outstanding surveys. So some people aren't here, so we've already slacked them about it. But for people who are sitting in the room who have not filled out the survey yet, please, it should be in the email that you use to sign up to the course with. Please fill that out. It should take 5 minutes, no more, no less. And always remember, we have cupcakes. I promise you those weren't correlated. All right, so we'll walk around to answer questions, but please work on a project or a homework you haven't done yet, or something to help catch you up or move you forward. We'll come around to help.